Alrighty, let us start. So we're continuing. We're going to wrap up Newton's third law today. Do circular forces. And then in terms of expected content, that'll be it. I might say a little bit extra on non-inertial forces, but that will be an optional component. So let us start, though, first with a review question from a previous exam. Stuck to your seat. You are 70 kilograms sitting in a car seat without a seatbelt on. Foolish. Your car accelerates to a stop at a rate of 1 meter per second squared. If your hands are not on the steering wheel, what causes you to come to a stop? And if the coefficient of static friction between you and the seat is a half, do you move in your seat? I.e., do you fly forward and smack your face on the steering wheel? All right, so the setup is you are sitting in a car seat that is moving forward, or to the right in this case. You are decelerating or slowing to a start. That implies that the acceleration points in the opposite direction. And the question is, what is causing you to come to a stop? So when you press on the brakes, the brake pads on your car are touching the wheels of your car. The contact is between the brake pad and your wheel. When you press the brakes on your car, and a force is applied to your car, but not to you. Your brakes are not slowing you down. But obviously, as long as you don't stop too abruptly, you slow down with the car as well. So what is slowing you down? Well, if I had to ask myself, I would say there's some force I'm in contact with. So if I define my system as myself, I'm, of course, weighing down on the seat. The seat is in contact with me, so it points back up. And if those were the only two forces, notice there's nothing in the horizontal direction. There is no force that can provide the acceleration that points to the left, like what I've drawn. If these were the only two forces, you would not decelerate at all because there's no horizontal force acting on you. So while the car slowed down, you would just keep going at the same velocity, Newton's first law, and smack your face into the steering wheel. But what is actually happening is you are in contact with the seat, and that seat not only has a surface force pointing perpendicular away from the seat, there's also that parallel component, which is friction. So there's a friction force that is trying to provide you with the same deceleration or acceleration in the opposite direction that you're moving. And if we say that if you don't move, right? And by don't move, I mean don't move in your seat. Then that's saying something about the amount of friction that is being exerted. Let's see, seat and static both start with an S, and that's unfortunate. So I'll write F seat. So if friction is able to decelerate you without you slipping, that means that this friction you're feeling from the seat must be less than the maximum possible amount of friction that static friction can provide, else you would start to slide. All right, so given this force diagram, and let's see, I will define up and to the right as positive. Sum of the forces on me equals my mass times my acceleration. I could look in the y direction, and that says that gravity is pulling down on me, so I would say minus mg, plus some contact force with the seat, maybe we call it a normal force, equals my mass times my acceleration in the vertical direction, but I'm not moving up or down, so that is 0. The normal component in this case is just my weight. In the horizontal direction, the only force that I drew in my free body diagram is the friction from the seat. So I would just say negative F seat, negative because I'm assuming it's pointing to the left, equals my mass times my acceleration, which we said is minus my mass times 1 meter per second squared. Minus because it's pointing in the negative direction. So then the magnitude of the friction force from my seat is then 70 newtons. 70 kilograms times 1 meter per second squared. That is the friction force that is necessary for me to decelerate at 1 meter per second squared. If this is less than the maximum that static friction can provide, then I don't slide. Or I'll say then no slip. So I was asking, is 70 newtons less than? And now we have to ask, what was the formula for this again? The static coefficient times the normal component of the contact force, which in this case we showed was just mg. Not always the case, of course, but in this case it is. Let's see. G, I'll round up to 10. Just keep the numbers nice. So I'll put a little approximation there. So this, in this case, is about 350 newtons. 70 is less than 350. So therefore, I do not slip in the seat. My seat is able to decelerate me at 1 meter per second squared, and I am fine. If the acceleration I experienced was even higher, notice what that would do is it would increase the friction that the seat has to, or the force rather, from friction that the seat would have to provide. It wouldn't just be 70 newtons, it would be something larger. You can imagine if the acceleration is high enough, eventually that what is now 70 newtons would exceed 350, in which case I would begin to slide in my seat and I would go face first into the steering wheel. Also notice how I stated that my hands were not touching the steering wheel. Obviously, if I was touching the steering wheel, that would be another contact force that would be pushing back on me. And that could also help provide some of the acceleration to bring me to a stop. All right, good. So we started talking about Newton's laws last time, or Newton's third law rather, last time in lecture. And as a reminder, remember Newton's third law says that all forces come in pairs. Every force, be it contact or long range, has another force somewhere in the universe that is its pair, its companion, such that those two forces that make the pair have equal and opposite. They're equal in magnitude and opposite in direction. Between contact forces, we're starting to get some intuition for why that is the case. I push on the wall pushes back on me. I push on both my hands. This hand is pushing on this hand is pushing on this hand. They are pushing with the same force through their contact. A misconception is, for example, that you have a giant semi-truck that crashes into a tiny little car. Clearly, the tiny car has the worst day during that event. The tiny car is destroyed, while the semi-truck might not be damaged at all, or really damaged that much. So you might want to say that the semi-truck exerted more force on the little car than the little car did on the truck, but that's incorrect. They both exerted the same amount of force on each other. But in that case, since the semi-truck is just so much more massive, that similar amount of force had less of an impact on the giant semi-truck compared to the very low mass little truck. And we'll look at another example of that with the Earth and the Sun in a little bit. Speaking of which, long-range forces also have this sort of pair companionship. You know, I realized I said there was an animation in the last lecture, and then I never showed it. So here's that animation. Even gravity has, you know, a gravitational tug from one body on another, like the Earth pulling down on this apple. That has a force companion where if the apple is being pulled down by the Earth is also being pulled up by the apple. The apple is pulling on the Earth just as much as the Earth is pulling on the apple. And again, that seems so counterintuitive. The apple is the thing that's doing all the motion. We don't see the Earth flying around because I'm throwing apples into the air. But again, it's because the Earth has so much more mass that we don't really notice an acceleration on the Earth from the apple. Where the apple being so little in mass, it has a quite large acceleration as a result of the tug. But that nonetheless means that as the apple falls to the ground, we think of it as the Earth is pulling the apple to the ground. The apple is also, in a sense, pulling the Earth up towards it. You are pulling the Earth up towards yourself just as much as the Earth is pulling you down and keeping you grounded on the floor. When we look at, say, the Earth around the Sun, or two stars orbiting each other, or Pluto and its moon Charon orbiting each other, those mutual gravitational pulls are equal and opposite in direction, and so as a result, both objects are actually moving around. Even though, like what you see at the bottom, it looks like, you know, that might be the case of, say, Earth and the Sun. Actually, it's probably more like Jupiter and the Sun. Where the little thing, Jupiter, looks like it's doing all the motion. Where the big, more massive Sun, which is 1,000 times more massive than Jupiter, 1,000,000 times more massive than the Earth, the Sun does not end up moving that much, even though it is feeling the exact same amount of force being pulling on it. Jupiter, or the Earth, being so much less massive, they, as a result, have very large accelerations as a result of that force, compared to the Sun, which just wobbles. And our Sun does wobble. This is actually, in the 90s, was one of the only ways we had to find planets outside of our solar system. The way we discovered the first planets outside of the solar system is that astronomers would look at distant stars and notice by their light that the stars were wobbling. And therefore inferred, well, if the star is wobbling, stars don't just wobble because. They are wobbling because something must be pulling on them. And so they could measure the amount of wobble they see from the star and are able to essentially work backwards and figure out that, okay, if we're seeing that amount of wobble, that means there is a planet that is this big and this far away from that star. The 2019 Nobel Prize in Physics was awarded for this work. So last year, Mayer and Questlaz won the Nobel Prize in Physics for essentially Newton's third law. Using Newton's third law, looking at distant stars, noticing that they're wobbling, that must result from a force, and inferring some of the first extrasolar planets that were out there. We now, of course, know of thousands upon thousands using different techniques. But that was one of the first ways that we could study and find extrasolar planets outside our solar system. All right, you're walking forward. What is allowing you to accelerate in the forward direction as you run or walk? You push down on the ground. The ground, therefore, pushes back on you and pushes you forward. It's the ground that's making you move. Again, Newton's third law. Let's do a few examples. The problems with Newton's third law can get really interesting, but also they become way more complex. Let's suppose you have this weird Tetris-shaped block that has a mass of 4 kilograms, and you press on it with a horizontal force of 10 newtons. Let's ignore friction. What is the resulting acceleration on this Tetris block? Well, the free body diagram is quite simple. There's your force, your push. There's, of course, their weight and the contact force, which aren't going to actually matter for this problem if we stick with the horizontal. So in the x direction, the sum of the forces on the block equals the mass of the block times the acceleration of the block. There's only a force from your push that is acting on the block. If I let's define up and to the right as positive. Therefore, this is 10 newtons equals mass times the acceleration in the x direction. Put a little sub x. This then is 10 newtons divided by 4 kilograms. 10 divided by 4 is 2.5. 2.5 meters per second squared. Plus 2.5 meters per second squared. The acceleration is to the right. Probably not too surprising. And really had nothing to do with Newton's third law. But now let's consider this. Suppose it is now revealed that this Tetris block is actually 2 blocks taped together. So that it's actually one little block that's 1 kilogram and then a bigger block that's 3 kilograms. Now what's going on? Well, in this case, now we have 2 systems. System 1 is this little block, and then system 2 is this big block. For the little block, there's a push, the force of the push. It's of course touching the ground, and there's a surface force, which again I'm not going to care about for this problem. But notice now the little block is touching the big block. So there's also a contact force between the blocks. I'll call this force, big. If this is the big block and this is the small block. Smooth. Then we could look at the big block and ask what's going on there. It of course has gravity and it's touching the surface. But now if I look at what's touching it, I'm not pushing on the big block with 10 newtons of force. But the little block is touching the big block. So there is a force from F small. The small block is pushing on the big block. And that's it. Those are the forces that are acting on the 2 systems. However, we can make one more realization when we realize that these 2 objects, these 2 contact forces, are a Newton third law pair. And therefore, I can also write F small is equal and opposite to F big. Here I write a minus sign with the vectors just to represent that whatever direction F small points in, F big points in the opposite direction, but has the same magnitude. So I would say with Newton third law questions, you first identify all the forces. Then there's now an additional step where you identify all the Newton third law pairs and write down those relationships in the margin, because you will need them when you do Newton's laws. All right, so now the question is, I can now do F equals ma And let me first do it for the small block. And let's only look in the horizontal direction because that's what matters. That's all that's going to matter right now. All right, looks like there's F push plus F big equals the mass of the small block times the acceleration of the small block. Then for the big block, sum of the forces on that block equals the mass of the big block times the acceleration of the big block. That implies this F small equals m big times a big. There's only one force acting in the horizontal direction on the big block. Now we could think, are there any other relationships that are necessary? Why did we solve that Tetris block version before? And we got an acceleration, 2.5 meters per second squared. Is that useful at all? It is, because I claim that both of these accelerations must be 2.5 meters per second squared. If they weren't, there would be relative motion, even though they both might be moving to the right. If there's a relative acceleration, that could cause them to, say, separate. Maybe the one in the front kind of zooms away while they both are moving in the same general direction. Or, if, it's kind of hard to imagine, or if the accelerations were different, they might get crammed together in some way. Neither of those are really plausible, but we can say that A big, because if they separated, for example, then the contact force between the two blocks would vanish. F big and F small would go to 0. And therefore, the big block would stop accelerating at all. Okay. So that's a step forward. So I can actually go back to these and I'll just erase the subscripts because they're both the same acceleration. I actually, in this point, I don't even need to know that it's 2.5 meters per second squared. Let's actually assume not. Let's just take for granted that they're the same acceleration, but I might not necessarily know that it's 2.5 meters per second squared. So the next step would be to employ Newton's third. So there I can write F push plus F big equals m small a. And then instead of F small, I can write this as minus F big. So I'm using Newton's third law in that relationship. You might ask, why am I doing this? Because now I'm able to better combine the two equations. I could go back, what do I know? I know this, I know this, I know this. I don't know A, and I don't know F big. But if I wanted to solve for either of them, I could use both of these equations together. So this implies F big is m big times A. Now I'm going to plug that into the top one. So that says F push plus F big, but we just said F big was minus m big A equals m small a. Now we're cooking, because now I know everything in this expression except A. I can solve for A. So this says F push equals, looks like m big plus m small times A. Notice I've yet to say anything about the coordinate system. I've been working entirely with vectors. That minus sign you see flying around is a minus sign that came from Newton's third law. Nothing to do with coordinate systems. But now, finally, my last step, I can say, okay, we said this was 10 newtons equals the sum of the masses, which is 4 kilograms, equals the acceleration in the x direction. Lo and behold, we again get that the acceleration is 2.5 meters per second squared, plus 2.5 meters per second squared. We get the same answer, which I claim would have been ridiculous had we not. But this also is a nice example where it goes to show why, when we did free body diagrams and force diagrams before, that I said objects cannot act on themselves. An object cannot accelerate by acting on itself. And this is why. Because of Newton's third law, all those internal interactions cancel out. So if I go back to my Tetris blocks, if this were my system, and I say that this is my system, and there's an F push here, like what we did up above, like what we did here. In this case, if I identified all the forces acting, I told you to only do forces that are acting on the system. But maybe you accidentally include these internal forces as well. Then you would say, okay, there's F push from outside. There's gravity, of course. And there's the normal force. But then maybe you want to include those internal pushes and pulls as well. Then you would have something like, then there's also F small, and then there's also here F big. But we just argued that F small and F big are Newton third pairs. They're equal and opposite. So this plus this adds up to 0. They cancel each other out, and you're again left with what we had before. That is why when I say objects can't act on themselves and cause an acceleration, because by Newton's third law, if I push on my arm is also pushing back on my hand. I cannot create a net acceleration for my entire body by pushing on myself. All right. And then finally, that aside, if I then wanted to know, say, how big, what magnitude is F big, for example, then I could go back to that expression I had above, which we said that was equal to m big A, which is then minus 3 times 2.5 overall newtons. So then this is negative 7.5 newtons. F small, therefore, is plus 7.5 newtons by Newton's third law. The small block is pushing on the big block with 7.5 newtons of force. You might say that's less than 10. And if you think about it, that must be the case, because if both objects are going to accelerate to the right, there needs to be a force that provides that acceleration. And to just accelerate the big block, which has only 3 kilograms, you do not need 10 newtons of force to get it up to 2.5 meters per second squared, like what was required up here when we were looking at 4 kilograms of stuff. We needed 10 newtons to get it to 2.5. Down here, the big block, the block with only 3 kilograms, you therefore need only 75% of that. So you need 7.5 newtons rather than 10 newtons. And then notice that also means the net force. What is the net force on the small block? F net, F small net, say. Then looking up above, we said that was F push plus F, the force from the big block. That was the sum of the forces on the small block. But that's plus 10 minus 7.5 newtons equals 2.5 newtons, pointing to the right. You only have 1 kilogram that you need to accelerate up to 2.5 meters per second squared, so you don't need all 10 newtons of force, you only need 2.5. And those internal actions, those Newton third law pair interactions are what's kind of regulating what's going on. I love Newton's third law. Let's see. Maybe I can do one more. I didn't do the one with the ball in the earth. I meant to do this first. Let's take the earth. Let's take my little apple, which is about 0.1 kilograms, which I'm picking so that I can approximate the weight as 1 Newton. So mg is approximately 1 Newton. I'm rounding 9.8 up to 10. Then the Earth has a mass of, come on, PhD in astronomy, 6 times 10 to the 24 kilograms. By the way, this little circle with a plus, that's the astronomical symbol for the Earth. So if I write that without explanation, that just means the Earth. I might also use this with a little dot, which is the sun. Anyway, here's the question. I release an apple from 2 meters or so in above the ground. It falls towards the ground because of the gravitational pull between the Earth and the apple. The apple seems to be doing all the motion. It accelerates at 9.8 meters per second squared. We can measure that and verify it experimentally. But by Newton's third law, we just said that the apple is also pulling on the Earth. Is the Earth accelerating at 9.8 meters per second squared? If it is, we would notice. Since we don't seem to notice, that suggests it's not. Let us actually calculate. How much is the Earth accelerating while the apple is falling towards the Earth? All right, so I have two systems. I have the apple, and then I have the Earth. For the apple, it is being pulled down by the force from gravity from the Earth. As a result, anticipating where we're going with this, the Earth therefore feels a force due to gravity from the apple pulling up. And these are Newton third pairs. Reminder from last lecture, like forces form pairs. So gravitational forces are paired with gravitational forces. Contact forces are paired with contact forces in terms of Newton's third law. Okay. We could look at, let me define up as positive. We could look at the sum of the forces on the apple, and that equals the mass of the apple times the acceleration of the apple. In that case, the sum of the forces, in this case, is Fg from the Earth equals the mass of the apple. And we know experimentally that the acceleration that the apple experiences is minus g in this case, minus based on my coordinate system. Which is about negative 1 Newton. If it's a 0.1 kilogram apple. Now I can do the sum of the forces on the Earth equals the mass of the Earth times the acceleration of the Earth. The sum of the forces on the Earth was the force of gravity from the apple equals mass of the Earth, acceleration of the Earth. But Newton's third law, this is the same as minus the force of gravity from the Earth on the apple equals the mass of the Earth, acceleration of the Earth from the apple. This left-hand side is minus m apple g equals the mass of the Earth, acceleration of the Earth. And let me just point this out just so that it's super clear what's going on. This minus sign was introduced because of the Newton third pair, equal and opposite forces. This minus sign was introduced because of the coordinate system. And that equals the mass of the Earth times the acceleration of the Earth. Let's zoom over here. Oops. So that implies the mass of the apple times little g is equal to the mass of the Earth times the acceleration the Earth experiences. All this is positive. It points upward as expected. But notice then if I solve for the acceleration the Earth undergoes, it is not g, but it is g 9.8 meters per second squared times the mass of the apple divided by the mass of the Earth. This ratio is incredibly tiny. It's something like 1.6, I think, times 10 to the minus 26. So that if I plug in 10 for g, this is on order something like 10 to the minus 25 meters per second squared. So the apple falls down at it and accelerating at 9.8 meters per second squared. The Earth accelerates up at 10 to the minus 25 meters per second squared, which is a little bit smaller than 9.8. You know, what can a body detect? A body can probably detect something along the lines of, 1,000th of a g. So 10 to the minus 2 times g, not 10 to the minus 26 times g. I think the record for the lowest accelerations detected in a laboratory is something like 10 to the minus 15 g. So this is 11 orders of magnitude smaller than what we could best detect in a lab with fancy equipment. So we do not feel the Earth move as a result of the apple falling towards the Earth. And that's probably for the better. Newton's third law. So if we had to think of kind of what is the strategy, what is the general strategy, since this is essentially wraps up Newton's laws, the general strategy here really is free body diagram. Step one, free body diagram, force diagram, free body diagram. Identify all the forces, said another way. Step two, identify all the force pairs by Newton's third law. Step three, write down F equals ma for all of the systems, which might involve multiple dimensions as well for each system. Write it down as vector expressions, so just adding up a bunch of vectors, no minus signs to be seen. Next step, the new step, use Newton's third law to switch some of the forces to be negative the other forces by the Newton third law pair rules. Like what we did right here. Oops, that was meant to be a highlighter. Like when we went from these to these, we used Newton's third law to replace one of those vectors with the negative of another vector by Newton's third law. Then only finally do we introduce the actual coordinate system where we put in whether forces are in the positive direction or the negative direction. Solve for the quantity you need. The sign of whatever your answer is will tell you whether or not your guesses were correct, whether it's in the positive or negative direction, etc., etc. The math will never cheat you as long as you systematically set it up like that. For no matter what problem there is, no matter how many forces, what kind of forces, that approach will always work. Let's see, I was going to do another problem of hanging Christmas lights, but I'm already at 40 minutes. Well, let me do circular motion, and then depending on how much time I have, I might come back and do another Newton third. Let's see. Nice over. Circular forces now. We've already dealt with circular motion. Remember that circular motion, particularly if you are moving in it's a terrible circle. If you are actually moving in, I give up. Pretend that's a circle. If you are actually moving in a circle, you have some velocity that points along your path, tangent to your path. And to be moving in a circle means that your acceleration that you're undergoing is perpendicular. The perpendicular component, remember, changes direction. So you can get circular motion if you always have some sort of repetitive, maybe it's an ellipse, depending on if you're speeding up or slowing down. You can get circular motion, but that requires a perpendicular component. And then recall, if acceleration is constant and always perpendicular, then you get uniform circular motion. With the acceleration due to circular motion given by, I might write this as v squared over r. I might throw a minus sign in there depending on my coordinate system. I'll take it out. Rather than write a minus sign, I'll just write, and it points to the center of the circle. That is centripetal acceleration. We now know, having studied 2 chapters of Newton's laws, that accelerations result from forces. So we can now define what a circular force is. And it's actually quite straightforward. There's nothing new about circular forces. It's not a new force in addition to friction, in addition to Hooke's law. Circular force is just whatever force provides circular motion. If there's a force in your problem that is always pointing perpendicular to your velocity, for example, that force is what then will cause your object to move in a circle. It is not a new force in addition to everything else. Oh, that's a good circle. For example, the sun and the earth. The earth is moving in a approximately perfect circle around the sun. It has some velocity, and it is a result of the gravitational tug on the earth from the sun. So there is an acceleration that results, and that acceleration is a result of gravity, a force due to gravity between the sun and the earth. Not 9.8 meters per second squared, of course. That is only for when you're near the surface of the earth. It's something quite different. But nonetheless, the sun is pulling on the earth with an acceleration that points perpendicular to the earth's velocity. So as a result, the earth's motion is constantly changing direction, but the earth in this case is always moving at roughly 30 kilometers per second, which is the speed of the earth as it orbits around the sun. So in this case, the circular force is just gravity. Gravity is what's causing you to move in a circle. When I have this ball, and I spin the ball in a circle, it is undergoing circular motion. Therefore, there must be some center-seeking centripetal force that is causing that acceleration. In this case, it is being caused by the string or the rope. There is a tension that is being created as I spin this object around, and that tension is always pointing towards my hand, and then the ball is moving in a circle around that center point where my hand is. So here, the circular force would be whatever the tension is in the string. When you make a turn on your car, I come up to an intersection, I make a left-hand turn. What is causing the car to turn? Not the engine. The engine is only giving you accelerations forward, or I guess if you include the brakes, backwards. The brakes and the engine are only saying what you can do going forward and backwards. It is not providing a force that is perpendicular to the car and allowing the car to turn. In that case, when you turn the wheels of the car, let's see how well I can draw this. When you turn the wheels of your car, so here is perhaps my boxy car. When my wheels are parallel, that is when I move, say, forward. When I turn the wheels of my car, in this case to the left, the car is trying to move forward. But notice now the wheel, which wants to roll very naturally, and if the wheels are aligned with your velocity, they will roll very naturally. But then if the wheel is now turned this way, that causes it to essentially try almost skid across the ground. That, of course, sounds like friction. So what happens is when you turn the wheel of your car, what you are doing is you're creating a friction force between your wheel and the road. And that friction force operates, in this case it's static friction. The static friction force points towards some center of a hypothetical circle that you are turning around. That, as a result, turns your car. It is the friction between your wheels and the road that turns your car. Which, again, is why, if it's raining and you start to hydroplane and you start turning your wheels, you still just keep going forward because there's no friction anymore between your wheels and the road. So even though your wheels are turning in a different direction than the car is moving, the lack of friction causes you to just keep going forward. And if the static friction is not enough, that is when your car actually does skid. In which case then it's kinetic friction that is trying to turn the car for you. So again, circular forces, it's not a new force. You just have to look to the problem of what you're analyzing to try to understand what force in the problem is providing that circular motion. Suppose I have a table, I could have a table like my desk, and I have my ball on a string. If I were to write this down, I could spin it in a horizontal direction on the table. And I'm doing this on the table just so that I don't have to think about gravity and all of that stuff. So I could spin a ball attached to a string horizontally on a table. In that case, it would be the tension of the string that is playing a role here, that is causing this circular motion. So if I were to do a free body diagram, circular motion gets a little tricky with, or free body diagrams rather get a little tricky with circular motion. Because I might say the only thing acting on the ball, and then of course is gravity and the table, which I don't care about right now. But in the plane of the table, it's really only the string that is acting on the ball. But for circular motion, it's hard for me to draw an arrow that represents a circle because the direction of that tension is constantly changing. That's why it provides circular motion. The acceleration is always perpendicular to the velocity. So in this case, I usually just make a note to myself and I say that this is pointing toward, say, center of table or something. So I might say that that's, some sort of radial vector. It's pointing towards the center of the circle in that case. And then the sum of the forces equals the mass times the acceleration. Let's see, let me define towards the center of circle. Let me define that as the positive direction. Again, it's a little trickier with circular motion when you're playing around with coordinate systems. But then that says the tension in the rope equals the mass of the ball times the acceleration of the ball towards the center of the circle. But we have the added bonus of knowing that the acceleration in that case is just v squared over r from the last chapter. So this allows us to directly connect the force, the velocity, and the radius along with the mass of the object, if you wanted to. We're taking the centripetal acceleration from before, and when there is centripetal acceleration, we can connect it through forces, of course, through Newton's laws. But now we have an expression for the acceleration, v squared over r. Okay. Suppose there's a roller coaster that has a vertical loop. I could ask, at various points along the loop, what is providing the circular motion? In this case, it is not uniform circular motion, which, if you've ever been on a roller coaster, is probably obvious to you. You slow down as you go up, and then once you get over the loop, you seem to speed up as you go back down. And usually they'll design it so it almost will feel like you're not going to quite make it, and then you make it, and then you speed back up. So we can ask, what are the forces acting on my little roller coaster car? And what is providing me circular motion versus just speeding up or slowing down? So let me redraw the loop. Oh man, another perfect circle. Then here's the start and end. So I could ask, when the car is here, what's going on? When the car is here, what's going on? When the car is here, what's going on? And then when the car is here, what's going on? In all of these cases, gravity always points downward. There's always a gravitational force pointing down. But if I were to draw a blue box around my roller coaster cart and look at what forces are acting on the cart, there's not only gravity from the earth, but it is in contact with the track. So there's a surface force from the track. But notice in this case, it constantly is changing directions. At the bottom, the track is pointing, it's pointing away from the track. Here it's pointing away from the track. Here it's pointing away from the track. And here it's pointing away from the track. So I might call this F track, F track, F track, and F track. So what is causing the circular motion? In this case, it looks like it's the track that is causing the circular motion most of the time. At the bottom, the thing that's pointing towards the center of the circle is the force from the track. On the left and the right-hand side is the force from the track that is pointing towards the center of the circle. And at the top is the force from the track and gravity that is pointing towards the center of the circle. So the track itself, so track and sometimes gravity. Point towards the center of the circle. That is what gives you the circular motion, or what allows the cart to keep changing direction as it goes around the circle. And then you can notice at some points, so in the top case here, gravity and the track are helping the car go in circular motion. Yeah, I guess I could also write the velocity vector just to make it clear as well. Here the velocity is pointing this way, the velocity is pointing this way, and then this way for... So we could look at each of these spots together. So in the top, both gravity and the track are pointing perpendicular to the velocity. So both of these forces are only changing the direction of the roller coaster. Similarly here, they are both perpendicular to the velocity, so they both are only trying to change the direction of the car. But in this case, since it's really only the track itself that is succeeding, since it's allowing, this must exceed this in order for a circular motion to occur in the way it's drawn. Here, the track is causing the velocity to change direction, but in this case, gravity is pointing anti-parallel to v. So in this case, this is where, so then gravity, there's an acceleration that's pointing downward. So in this case, I would say that gravity is slowing down the roller coaster car. In this case, the track is changing the direction because it's perpendicular, but gravity is pointing in the same direction as velocity. It is helping to speed up the roller coaster car. Since the amount of force pointing towards the center, and therefore the acceleration experienced towards the center, is not uniform, this is not uniform circular motion, but it is nonetheless circular motion. And I think one of your labs you're going to do the conical pendulum, where you have, a pendulum. Again, it's not a complete circle, but it's kind of part of a circle. The bottom part of a circle. This is like the pendulum of a clock. It's tracing out an arc of a circle. And again, what is causing this motion? There is a perpendicular component that is along the string that is providing only a change in direction. And without friction, it would do this forever. Grandfather clocks are designed to more or less be able to tick indefinitely. But sometimes you have to wind it up because of friction. And I think you're doing the conical pendulum, so it would be something that looks like this. So it kind of traces out a circle. But again, that motion is because there is we could actually write that down real quick. Suppose you have a ball that's kind of going in a circle. And maybe, or kind of like, what was that game from like childhood playgrounds, where it was a big ball and a string, and the goal was to like wrap it up or like knock it back and forth, and the ball would go around, but it'd be stuck onto the string, so it would always kind of stick around, and you had to like hit it so that it wound up on the rod or something. Blanking on what that game was. Same sort of setup, really. You can imagine a setup like that. So suppose you got it started so that the ball is just moving in a circle, so it's tracing out a circle on the table. We could analyze that circular part, because if it's moving in a circle, there must therefore be some component that is pointing towards the center. even though the tension might be along, some third dimension that goes into and out of the table. Right? There's some tension that's pointing up away from the table. But there's some component of that tension that points in the plane of the table and is always pointing towards the center. It's this component, which again you could just find by SOHCAHTOA, provides circular motion. The other part, the part that points, perhaps directly upward, that part is then what is balancing gravity, which is pulling the ball downward. Where am I? Exactly an hour. All right. That is all I really want to say about circular motion. Nothing new, just now you have to think about what is providing the circular motion you observe. It is not a new force itself. Alrighty, I think I will leave it there for the day.